talk to you and go through some of the work that we've been doing a lot here lately at Vectorize. Is we've been thinking about this whole domain of agent memory and thinking about how we can move from this world of just simple recall and retrieval to something that's more powerful. And so let me start off by saying, we're at a very interesting transition point with agents, because most enterprises out there are using AI across the board in some way, shape, or form. And maybe it's not pervasive. It's maybe not at the transformational level for most organizations quite yet, but we're close. And I think we can all start to see that and sense that from a lot of the things that are starting to emerge. Whether or not you think OpenClaw is legit or not, or it's mostly hype. I think it's a big percent hype, but at least somewhat real. I think it at least is starting to give us a glimpse at what's coming, right? Whether or not sort of we're here right now, I think it's kind of inevitable that we're on this track. But there's a reason why we see so many issues in terms of agents actually kind of delivering on the promise, and that's because most of them are stateless. You'll see them work really well one time and then fail the next, because you deal with a lot of these problems with agents around inconsistency, around hallucinations, around cognitive overload, and around just getting stuck trying to solve more and more complex tasks. And a lot of that has to do with memory. So, the promise, like, why are we so excited about agents? Why do we think they hold so much potential? Well, we think they hold so much potential because, eventually they should be able to handle these open-ended tasks. They should be able to act and operate more like an AI employee. And if you think about one of the main sort of gaps that we'll be talking a lot about today, it's going to be this aspect of learning. Why is it that a human employee gets better over time at their job? Because they learn, they make mistakes, and then they learn from those mistakes. Our agents don't do that today, at least not without a lot of effort on your part. And certainly it's still a tricky problem to solve on your own if you want to have an agent that has access to lots and lots and lots of different tools the way we do as humans, and make sense of those to solve complex tasks. That's not an easy undertaking. So when we think about this from an example of an agent, you probably have encountered this before, where your agent ends up making the same mistakes over and over again. You might correct it, you might try to update your system prompt, and that's usually what most people do. You kind of are the feedback mechanism where you watch your agent makes some mistakes, you go back, and if you don't go back and make changes to your system prompt, the agent will make those same mistakes over and over again. And once you start making the system prompt, it starts getting long and complex, and it can kind of cause a lot of problems there. So let's talk a bit about why agents fail. So if we get down to sort of the brass tacks about why agents struggle in these areas, we can start to identify certain characteristics of agents that are responsible. So one of the first things people try to do is they'll put in place this idea of episodic memory. And with episodic memory, it's going to give you some kind of understanding of your session history. And that's usually a good start. And then we start to get, once you have that in place, you realize, well, that didn't actually solve a lot of the problems that my agent has. It still doesn't have any way to accumulate the knowledge over time. There's no feedback that's happening here, where my agent just on its own, as it attempts to solve tasks, is going to get better at those tasks by virtue of it making mistakes and then learning from those mistakes and then improving as it goes. And so we want to have some way of letting our agents accumulate these skills, some way of the agent taking feedback from either its own experiences or from direct feedback that it gets from users or from us as AI engineers. And what we'd really like for it to do is to start recognizing patterns across those, so that it understands both the intent of the task better as well as how to execute those tasks better. So it just gets more and more successful the same way that we would, complete humans do, as we do. You go to install tile in your bathroom the first time and it looks pretty bad, but if you do that every day for a year, you get pretty good at it. And we want our agents to kind of go through that same process. A lot of us will start off in this world of RAG. And so I'm assuming most people on the call, probably all of you, but just in case there's a couple that maybe are newer to AI, are familiar with this term, RAG. The idea of RAG is what it stands for, is retrieval augmented generation. And that's just a way of saying that the LLMs have things that they don't know. So there's going to be a lot of knowledge gaps in the LLM, especially when it comes to your data, your organization's data. It doesn't know your specific policies. It doesn't know, thankfully, all of your, private, internal use only, data that you have in your organization. And so one of the ways that we can fill in those knowledge gaps is with RAG. And the idea is just simply that we'll retrieve information, we'll pull that information into our prompt, and then we will have the LLM, augment its generation process with what we retrieve. So that's kind of the origin of that term there. And it turns out that this works kind of okay for some things, but generally not memory. This is kind of like one part of memory. This is what we might sometimes call semantic memory, which you can think of like almost like the books on a bookshelf, right? It's like, I know I read about this somewhere. Let me go refresh my memory on exactly what that book said. This is kind of the LLM equivalent of that, which is RAG, which is I'm going to put my documents into a usually vector database, some type of graph database. I am going to query, and I don't really have the sort of accumulated knowledge from that I want to get with true memory. And so what's really missing from a lot of agent architectures is this idea of a learning loop, where we're going to have the agent take some action. Usually it's in response to a task. If you tell the agent, can you go, solve this problem for me? Maybe it's a customer service agent. That agent will make an attempt. It's going to act. There'll be some outcome. And what usually is missing is kind of these next boxes where we want to evaluate, how did that work? I tried these things. I tried to solve the customer's problem this way. Did I do a good job? Did I actually get the outcome that I wanted? Maybe I did, maybe I didn't. But in both cases, there's something valuable to learn. If it turned out that we solved the problem, well, that's great. The next time we see this problem, we should probably remember that this worked, and I should build on top of that understanding and continue on, relying on that technique. If it didn't work, again, I want to sort of reflect back and say, well, what is it about this task that failed? Have I attempted other things for similar tasks that worked in the past? How can I get a more complete knowledge? Which means that we really need to have a few things, right? We need to have a way to do this evaluation. We need to have a way to represent that learning. And then we need a way for our agent to actually update and adapt its behavior based on those learnings as we go. And this is important, not just in a theoretical sense, but in a very real sense. So this is from an MIT report that came out mid last year, kind of like mid-late last year, if I remember correctly. And you may have seen this stat, being kind of thrown around. It's interesting because the problem is not lack of AI investment. Organizations across the board, especially enterprises, are investing heavily in AI. And what they're not doing is they're not actually getting a very good return on that investment. So according to the research, they were actually saying about 95% of those organizations got zero return on their Gen AI investment. Now, where they do get some return at this point are kind of like the things we use every day, right? I want to write a document. Let me go to ChatGPT or go to Claude and have it, help generate this doc. The things that are really where organizations have really struggled is how do I take, how do I get to like that AI employee level of competence for my agent? How can I not just do a workflow, but how can I have my agent actually go and solve complex tasks? And it was interesting because the research concluded, the barrier here, you see at the bottom, you can read it, but it was really a failure of learning. Like there's no way for these systems to retain the feedback, to adapt and improve over time the way that people do. And so that was the problem that we here at Vectorize set out to solve. We wanted to solve this problem. We created an open source memory system. We're going to take a look at it here today, called Hindsight. And so the idea behind Hindsight was kind of twofold. One is we said, let's sort of imagine the way that human memory works, and what would that look like if we were to apply the same mechanisms into an agent memory system. And one of the first things that we realized is this gap between what most solutions do, what most AI engineers do if they're building something on their own, which is very recall oriented. How do I just recall pieces of information? And we said, I think the bigger thing is how do we actually make the agent learn? How do we build that learning loop so that agents get smarter and smarter over time? And you can see the GitHub repo down here. I did drop it in chat earlier. I believe it is pinned. So if you want to go take a look at the repo, or you want to bookmark that for later, please do. If you're feeling generous and want to leave us a star, we would, again, love you forever for your support. But let me talk a little bit about this idea of biomimetic memory. So biomimetic is just a hard to pronounce word that means we want to replicate some of the characteristics of biology in our technology. So we want to take the way that human brains work and we want to apply some of that to memory. So we started to think about this in terms of, there are a number of facets we had to consider in doing this. So one of those is just how do we actually encode this information? And by encode here, I just mean, persistence. Just like any data system. If any of you have have computer science backgrounds and remember all of our data structures, there's trade-offs to everything, right? Like sometimes you need a linked list, and linked lists are great if you want to insert something ahead or behind. You need two little updates to do that. Other times you need to access data in different ways, and depending on how you need to access that data, there are different data structures that are going to be optimal, that'll give you good performance and good performance both in terms of like speed and latency, as well as accuracy. So we had to think about this in terms of what are the right encodings for that data. And then we had to solve a bunch of the challenges that we solve kind of naturally as humans, right? If you tell a computer, you tell an agent, Acme is a prospect that we're trying to sell to today. And next week we come along and say, oh, Acme's a customer. You have no problem connecting those dots, like, oh, congratulations, you closed the sale. They went from a prospect to a customer. But in the world of agents and LLMs, if you see these two different conflicting memories, one that says, oh, they're a prospect, and one that says they're a customer, we needed a way to turn those raw memories into more consolidated pieces of understanding. And so we had to think about how we consolidate memories, which basically means how do you do some deduplication, because we didn't want to return a bunch of duplicate memories when the agent needs to fetch things. And then we also needed to solve and resolve these conflicts when they come up, which generally means trying to make sense out of pieces of information, kind of like puzzle pieces. We had to figure out how do these fit together, and then how do we put those into a form that allows the agent and the LLM to make more sense of those. And then how do we do that in a way that is fast so that when you need to recall memories, you can do it quickly and you're not sitting there waiting for your system to kind of go and do a full table scan of all the memories across all time. So the way that we did this is we organized our memory into this hierarchy and what we call memory networks. And so the idea is that as your agent is working, your agent gets its own experiences. So, and we'll see some examples of this coming up, where we have what we call world facts and experiences. And so these are the way that the agent perceives the world. This could be, chat exchanges that are happening with the agent. A person had a problem with their bill on the customer service agent, or, I've got a chat application and we're just chatting back and forth. What did the user say? Those are all the facts. And then what we want to do is we want to consolidate those into observations. So the observations are just our way of saying, let's remove any duplicates. So how do we, condense this down so we don't, fill up our context window with a bunch of duplicate information? And then how do we resolve those conflicts? And then because agents have ongoing, specialties that they need to understand, like, your customer service agent needs to understand how to interact with customers on a regular basis. What are our policies here? We have this idea of mental models, which is how we go across all the memories and have that agent actually learn and form a more complete understanding of the world and of its task and how to successfully get the outcomes that it wants. This is kind of the output of that learning loop that I showed you before. So how do we do this? So we start off with this idea of fact extraction. So when new information comes into the agent, we want to extract out the facts. And so let's say that we have a customer, has a complaint, and we want to give them, some limit, some adjustment. We might have facts about our world that says, well, you can only do that up to $25. If you want a retention offer, if you said, I'm going to cancel and you're a new customer, we're not going to give you a retention offer. These are kind of the world facts that we deal with. And then experiences might be, the things that the agent is experiencing. I tried to run I tried to make a tool call and it failed and it gave me back this validation message. That's my experience, the agent's experience, that it made the tool call and failed. And next time I should keep in mind, the max input of this is, so many characters, for example. All right, so we want to take all those experiences that the agent's having along with these facts, and we want to bring those together. And the way we do that is by constructing a combination of a bunch of different data structures. So the underpinnings of this have a lot in common with knowledge graph. So we'll take all of that data, we'll form what we call entity connections and semantic connections. So this is just how we understand how memories relate to each other. And then the other part that we do, I mentioned the observations and how we do conflict resolution. The way we do these, the way that we handle that is with this idea of time series and causal connections. And so if we see that there are memories that are related to each other, and we look at those as a time series, all of a sudden things like, hey, last week this customer was this company was a prospect, and next week this customer is a customer, all of a sudden we're able to link these things together through that time series, and it tells a narrative. And now not only does the LLM just kind of get these raw dumps of memories, it actually now has a way to think about these, to say, oh, this was the sequence of events that led to this company becoming a customer. And now it's very easy for that LLM to answer those questions and more accurately. Now, to make that work a little better, like I said, we do this process we call consolidation, which is how we take all of those raw memories and we consolidate it down. One of the problems that people often face with memories is this idea of like, what do I do when things, they conflict? I have this conflicting information, how do I resolve those? And the way that we do that is that we, again, try to build that out into a time series, and then we try to create a narrative. And if it turns out that there's just no real coherent way to explain the differences, then we rely on just a recency bias. And so we'll say, if for whatever reason, if it says, I don't have enough information to say, I used to live here and now I live here, and the person moved from here to here, we'll just say, here's where they live now. And that would be a fairly easy example for a time series, but I can't come up with a good example off the top of my head where we don't have the narrative. So, but when we do, that's our final strategy, I would say. So this leads into the idea of mental models. So mental models are the way for you to say, here are the things I want my agent, of all the memories, these are the kind of the things I wanted to really have a clear understanding of, and to look across all of the memories as they come in to form a almost like a pre-computed understanding of that topic. And we'll see how that works and how that actually turns an agent into, makes it perform better coming up. And there's a couple cases where you could think of, one might be something like customer service, where you want to say, I want you to get a good understanding of the way we do customer service. What can you do? What can't you do? And the idea here is to say, I don't want to go across, search all my memories every time. There are certain things that I want to have really fast lookups, and I want them to evolve over time as we get new information. And that's the idea behind mental models, is that we put these together on a per agent basis. And these allow the agent to form those understandings of things that they really care about. Now, we start getting here into now like the retrieval. And so, you say, well, how do you actually retrieve memories in a way that is going to give you back the most relevant information? Because that's a very tough challenge when it comes to agent memory, because there are different queries that are just better suited for different retrieval strategies. So what we do when we're building out those graphs, we actually create, I mentioned before, we created different representations. So those representations are semantic search. This is like your dense vector, things like you might associate with products like Pinecone or quadrant or chroma or anything like that. We have keyword search, which you might associate with things like Elasticsearch and others. And then we have this idea of knowledge graph, graph traversal, and temporal search. So what we do is we actually run all four of these because we don't know for each interaction with the agent what's going to give you back the best results. And so what we do is we run these in parallel, and then we use a reciprocal rank function, a fusion algorithm, along with a cross encoder. And so this is kind of like your traditional re-ranker. And then when we pull all of the results back, we do it in parallel so the retrieval isn't slow. And then we run it through here to say, how do we bubble up? You know, because I don't want to hand it all to the LLM. It's just going to fill up your context window. A lot of that's not relevant. So what we do is we use the cross encoder re-ranker to rank everything in relevance order. So I want to get all my memories now sorted by relevance, and then we'll truncate those based on a token limit that you set. And so you can say, I want the 5,000 most relevant tokens for my memory system. This is how we're able to pull those back because we use all these different strategies. And then depending on which one worked best for that particular query, the most relevant pieces bubble to the top. And it turns out that actually works out super well. You can see some of the benchmark scores. If you go to the GitHub repo that I shared earlier, it's pinned in the chat down there. You can see where our benchmark scores are. It's actually the most accurate memory system ever. So that was kind of cool that we did that. I mentioned the token budget. This is just how you can say, you essentially have a dial that you can turn here. So, you know, sometimes you want to optimize for, you know, cost and performance, and I don't want to send more tokens to my LLM than I absolutely need because, especially with bigger models, those can get expensive. And so this allows you to say kind of where in my recall, you know, do I want to optimize for more context, less context? And then this will get you a way to customize that so that you get back just the memories you need and just kind of the amount that you need. And then we start getting into this idea of the complete learning cycle, and kind of how those pieces fit together that I showed earlier, where as we have our agent performing its duties and trying to solve tasks or communicating with the user, you know, we are getting our output signal. Sometimes that output signal is fairly clear, like I tried to solve a task that somebody assigned me and I failed. And sometimes it's like I got a response from a user in a chat session. And so in both those cases, those are going to be retained as experiences. And then it runs through that pipeline that we mentioned before. So it's going to go through, it's going to create the different representations of that data, push it into the system, and then all of these are going to turn into these consolidated observations. So from your perspective, what you're going to get with Hindsight is going to be, you know, kind of for free, you know, just by virtue of you pushing in all your memories and you defining your mental models, you're going to get a very, you know, clear, you know, learning cycle out of your agent memory. So let me jump ahead. Let me kind of take a look here because I think this is really the interesting graph. This is a simplified graph from some internal research that we had done to see how we can actually make our agents smarter, like how does the learning work. And just like people, it's kind of interesting because there's a weighted bias that will happen as we're doing these memory processes. Whereas you get more information, you reinforce the lessons that the agent's learning. The agent tends to learn faster. It learns those lessons stronger. And so what we'll see is that you'll have a curve that looks like this, where without any memories, the agent will make mistakes. And then as we're building out those mental models, as we're building out our memory network, the agent will leverage those to learn, and it'll learn over time until it's getting better and better at its job. And let me just pause here for a second, and I'll see if we have any questions that have come up. And if not, maybe we'll switch over into demo mode. There's a couple questions. Okay. What is the difference between memory and grounding? Is memory, shifted up as I was reading it. Is memory simply well-organized ground truth? No, not exactly, but there's an overlap. So we have this idea of kind of these different types of memory that we can work with. And so there's the idea of what we call semantic memory. So when people talk about grounding information, usually what I think about there is I'm I want to ground my answers in some source of truth, right? And that source of truth is probably some, some documents, some policies, things like this. When we think about memory, memory is going to expand beyond that. So, you'll of course have things like short-term memory and working memory, but you'll also have this idea of like the conversation history. So this is like, what did we talk about before? And I don't so much want to ground my answers in that, but I want to, leverage that context along with the grounded truth. Usually when people say grounded, they mean I want to ground it in some source of truth. And they're usually talking about semantic memory. Also, this is kind of like what we used to call RAG. You'll hear, RAG, agentic RAG, semantic memory, kind of all solving, all kind of the same thing, honestly. Yeah, good question. So the model will always try to maximize the token limits. How do you manage accuracy versus efficiency? So the model won't always, what I meant by that token budget isn't that the model will try to maximize token limits. It's that we will truncate, we'll kind of get back a certain set of memories, and then we'll truncate them at that limit. So are we getting audio feedback? I don't know. Because we are. Nobody else is here, so I don't know. It's a weird message from Google. So what we'll do is we'll try to get back the most relevant memories, and then we'll just limit it by the total tokens that you want. So if you say, like, I want 10,000 tokens, like, we'll give you the most accurate 10,000 tokens. If you want 5, we'll give you the accurate 5. So perhaps a very simple prompt doesn't require to max out the context window. How do you balance it so every prompt doesn't get as expensive as your token limit? You just set the token limit to what you need. I mean, it's kind of it. You can, I mean, what you can do there, you can take an agentic approach to, Ro, this is your question. There's an MCP server for recall. And so this is done on a per query basis. So if you are using something like MCP, or you're just, using an agentic approach with a tool call to do a memory lookup, the LLM can decide how many tokens do I need. If it's a fairly simple request, it can try a smaller number. And then if you want it to go higher, you can give it a higher number. You can put your own limits on there based on your instructions to the LLM. Well, you do memory cleanup too, like a human too. Oh yeah, Joseph, I'm good at that. I'm very good at my memory cleanup. I clean up my memory of like where I leave my phone and my keys all the time. So we have kind of debated this. We don't have that in the product right now, in the project right now, but we are. That's only because we want a little bit more user feedback on that before we go and just decide what memories to start truncating. Okay, there's a lot of questions on here. I'm going to come back to those. We're gonna switch switch gears, and we'll kind of take a look at some stuff here. Oh, I was making sure this still worked. Right before the demo. Apparently it's running all around here. Let me do this. Okay, let me just refresh. Okay, let's start fresh with this guy. So what I have here is I have a little agent. So this is a package delivery agent. This is meant to show the agent learning, especially from a tool call perspective. There's a few different ways we can think about learning. We can think about learning, like learn how people want you to reply to them, like what are their preferences. You can have agents that, I'm showing you the wrong thing. You can have agents that learn how to solve tasks autonomously. You can have agents that learn your policies and how you want it to behave. This is one that's a agent we want to learn how to autonomously solve a task. And so what the task that we want this little agent to solve is we want it to solve a task of delivering packages to people who work in these 3 different buildings here. And so I just reset this. We are now using what we call a memory bank. So inside of Hindsight, we have memory bank, and you'll see that this will be everything you just saw in that presentation. So it has world facts, it has our experiences. It puts this into a graph. Right now we don't have any memories because I just wiped it all out. Oops, I forget that I'm not showing my whole window. We have Hindsight here, sorry. Here's our world facts, our experiences, observations. So right now our memory bank is empty. And this is what the Hindsight UI looks like. You can, if you go and download the open source, I'm running this locally right now on either Docker. I can't remember if I'm running this from Docker. I'm running this from the Python scripts, but it's very easy to run locally. And all this has right now is just three, kind of empty mental models. So these are the mental models for our agent. I said, I want our agent just to know, like, what are the buildings, where are the people, so that when you give it a random delivery, when you give it a delivery, I want it to get better at this job. And so I'm going to start off, we're giving a random delivery. We're going to try to deliver something to Brandon Lee in IT support, which is, right down here at the bottom. That was actually not too bad, by the way, for this guy to figure this out. He did, 16 steps. We didn't give the agent any context, right? The agent didn't know anything about this. It just knows I have some tools. I can move up, I can move down, I can check to see if the building, what office I'm currently at, and I can check to see, does the person I'm trying to deliver a package actually work here? And so after we did this, let's see, we should be able to come back in here now. Okay, so we've got like one world fact. We have one memory, really? And we have, okay, so we have some observations that have come in, and let's see. Our mental models have started to develop. So we have Brandon Lee, so it says, where's the employee? Brandon is now, first floor, building C. What's the building layout? It's starting to understand the building layout. And if we do this again, we give our delivery agent another, random delivery here, where is he going? Okay, so we got kind of lucky that time with that one. Let's maybe try a different one here. And what we should see is that as the agent goes and kind of does a random walk through these buildings to figure out, where's this person at? They're looking for the marketing department. There we go. So found it. That one took a little bit longer. And then as we are making these memories, what's happening behind the scenes is that every time the new memories come into the system, it's triggering an async process for us that's going to do that consolidation that I mentioned. Is going to take all the raw memories and it's going to push those into the observations, and then it's going to turn those into the mental models that that we define for our agent. So in this case, these are the ones for the building layout. So now we're starting to see, okay, like here's the building. We have 3 buildings. Here's what I found so far. We'll have a few other people that it's delivered packages to, and then we wanted to understand the route, the optimal route that it would take. So now if we take something like that, let's do Brandon Lee. Where's Brandon? That was his name, right? Brandon Lee. And we do a delivery to him. The agent should have a pretty easy time now. It says, okay, great. I've now, based on my learning, based on the fact that I know Brandon, I've delivered a package before, and my building layout that I know he works in IT support, this is the optimal route for me to get a package delivered to Brandon. And you can see here, like our, as a result, our learning curve, is working, and the agents learned and doing a better job. And let me come back over here and see if there's any other questions that have come up, especially related to this one. What do you mean by the agent improves? Is it a prompt change or memory system richer with context? Hopefully that explained it, Robert. If not, happy to take any follow-ups. But what you just saw there with that agent memory, the mental model is getting developed, the experience is coming in. That's what I mean by the agent actually improves. Like, it did a bad job the first couple times. It was going all around. It didn't know where to go. It didn't know how to do its job. But that last time, it was like, oh, I remember this. I'm going to go right to there. Any performance implications if memory gets larger? Yeah, for sure. Just like any database system, I'm sorry if I'm mispronouncing your name. Anytime you start getting a database that gets bigger, you're going to have to deal with all the typical database things that are going to come up in terms of just querying across larger things. And we have all the same techniques that we know and love around indexing and sharding and replication, things like that we can use, because it's all Kubernetes based, it's all Postgres based. So we've got a lot of those same techniques that are well established at this point are going to help you out in scaling a memory system. Let's see, we have a question from Jonathan. What are the key input, output, outcome, and counter metrics you are tracking to ensure the system is delivering value on the functionality of the user journey and the business outcome for the AI? Man, you packed a lot. That's like, Jonathan, congrats. That's the most information dense question I've gotten in a long time. Let me break this down. So I would say that I'm going to answer your question in a slightly different way. You still have, like, the memory system for trivial cases, you can get by with just dumping a bunch of memories into your memory system. But as you start getting into what you just described, you still have a little bit of work to do as like the AI engineer. I know we live in this vibe coding world where like the tools do everything for us, but there's still a little bit we have to think about in terms of, or at least have a good, we do have a hindsight skill. So you can plug the hindsight skill in and have the LLM solve this for you. But you have to think about, especially with mental models, we have sort of this notion in the system called tagging. And so you can tag memories. And this is partially how we can, there's a couple of ways you can segment your memories so that you can, like, for example, not see somebody else's memories and not have other people see yours. So we do that by separating things into either separate memory banks or this idea of tagging. And the idea of tagging starts getting into your question about how do you how do you track your inputs, outputs, and outcomes. So like what we might want to do in the case of like an agent that's solving tasks is we might want to tag different memories with a delivery ID. And then we might want to tag those outcomes with, was it successful or failure, or maybe like how many steps did it take for us to solve that problem. And then over time, we want to identify those KPIs the same way we would identify the KPIs for any other project, and then look at how we track those over time. Are we getting better over time? And what we would expect is that with the right memory, with the right agent, we're going to see that improvement happen. And that's really how we're able to deliver on that value and kind of get the, get the outcomes that we want. There's still some work for you to do. It's not kind of all, and that's just by virtue of the fact that like everybody's outcomes are a little different. So, it's not a one size fits all thing. If we did try to solve that in a one size fits all, it wouldn't work very good for you. Cleaning them up to make sure no unused memories. Yeah, part of that, Joseph. So I think Joseph's question is kind of like, it's along the lines of the one before about cleaning up unused memories. Maybe just a little bit about like little slightly different aspect on there in terms of retrieval, which is to say that part of what you get out of our re-ranking model is that anything that's not relevant automatically bubbles to the bottom and falls out of your token limit, which kind of keeps you from all the problems with context rot that you tend to get when you get a lot of memories, when you do context stuffing, those kind of things. Okay, so let's see. Let's just kind of scan. Are memory banks isolated from each other? Yes, they are. Very cool project. Does the scale and performance as data sets get larger? Yes, it does. I mean, yes, there's a limit for sure, Jay. Like, I mean, it's like everything, anybody that tells you they don't have a limit is, it's like when you tell an engineer like something is infinite, like nothing is infinite. So yes, there's if you try to store, the number of grains of sand in the world, numbers of memories, you're going to run into problems. But like I said, the good news is we have sort of all the techniques that we already know and love about scaling all these things. How is this different from using DuckDB? I don't understand that question, Jay. Like, these are very different things. How are mental models created, and what are they really? I think you saw that one there, Shipra, so I think we're good there. Ground of truth, somebody kind of weighed in on that. Thank you for that. We're looking at a PDF document. I don't think so. Maybe before you were. Maybe that was when I started the demo. How's this playing with LangChain and LangGraph? Yeah, so these are all pluggable. You can plug this in via MCP, which is kind of the easiest way to do that with a lot of these frameworks. We're also working on more official first-party integrations with those guys as well. So you'll see some more things coming out there soon. Let me see. Let me just do one quick thing here on a different tab. Because right before this, I kind of screwed up a couple things that I was going to show you. Okay, so luckily I didn't screw this one up. So let me switch gears again for a second and show another use case that we have here. One of the things that people run into pretty early on, one of the usually the first requirements people have around memory is this idea like I want per user chat history. I want this. I don't want to have to tell my LLM, my AI application, whether this is like a service application, whether it's a support application, whatever it is, the same information. I want it to remember what we talked about before. And so this is super easy with Hindsight as well. So I've got a little demo of this here as well. So I'll give this a name. So let's call this, who do we have? We had Jay, right? So we'll pick your name, Jay. And like, let's imagine here that you're chatting, with your personal chat GPT here, and you want to say something like, I want to buy a farm. I want it to be in the US. I want to grow profitable crops, and I want a reasonably priced farmland. Okay, so it's gonna, I guess I forgot my question on here, which was, where should I buy the farm and what should I grow on it? Okay, so Midwest profitable crops. Okay, so it's gonna come back here. Okay, so it's gonna say row crops, I'll say corn. Let's grow some corn on our farm. And where's it going to say? So Iowa. Okay, great. So let's just tell it now. Thanks. I just bought a 300-acre, farm in Iowa. And okay, so it's going to tell us, okay, we should do crop rotation. So yeah, corn is my primary crop. All right, that should be enough. Now, behind the scenes, as we're doing this, in our memory system here, we should now see there's a new bank here for J. And so we don't have any mental models yet, but we do have these world facts, right? So what's happening is that as we are interacting, it's pulling out the facts, it's doing that extraction. So it's saying, okay, you have a 300-acre farm, and you're going to grow some corn on it. So that's all fine and good. Now, most systems, when we would start a new chat session, would kind of forget all that. So if I say here, what is the best time to plant my crops? We should go back to the memory system, and it's now going to remember that, well, you're in Iowa. And ideally, the best time to grow, plant your crops is between April and May. And it's going to tell us like, well, soil rotation is important. So you might want to think about those, years when you're going to not grow corn or you're going to grow soybeans. You can do it a little later than you would. And so, we can test some of the aspects of the memory system here pretty easily. Like, for example, I mentioned that we had, graph representations. So one way we can get a graph representation to be the most effective retrieval strategy is with something like proper nouns, right? So let's tell the LLM here, I only grow crops on 200 acres and I have another 100 acres as pastures. I want to get livestock. What should I get? And hopefully it tells me horses. It didn't, but that's okay. I'm going to tell it I'm going to get horses anyway. I want horses instead. Okay, great choice. Okay, it didn't suggest it, but I still thought it was a great choice. I bought 3 horses. What should I name them? Okay. Let's see. Here are the options we have. We have Chestnut, Blaze, Shadow. Any preference? What should we name our horses here, folks? Haley. How about Haley? That's a good one. Bonfire? Yeah, okay. Bonfire is not a bad one. Thanks, Diedrich. Horse meat. Oh, Kevin. Kevin, you're my kindred spirit in terms of oh, you're terrible. You guys are terrible. But I share your sense of humor. Okay, we're gonna go with I'm going to name them. Whoops me. What was the other one we picked here? Bonfire. Okay. Bonfire and Storm. Okay. So I'm gonna name them that. Okay, perfect. Actually, horse meat's a good one. Only because it's not something that's one word, right? So it's kind of a proper noun that we have here. So let me see. Let me go back here. Let's refresh and start a new one. And I'll say this could actually get the LLM confused because it's going to think, are you trying to actually feed horse meat? What should I feed horse meat for breakfast? Okay, so it knew right away that what we're talking about horse meat, we're talking about a horse. It's one of the ones that we raised, and it's going to tell us, here's how we should do this. If I ask it a question like, what what equipment do I need on my farm? Now this one is going to be a little bit better suited to understand like a semantic search because, I want to know about my farm. My farm is 300 acres. And I might want to either we might get this information back, like because it goes to the re-ranker, we don't like on here. I don't know exactly which one of those parallel queries gave the most relevant results, but either graph or semantic search most likely. And it came back and said, oh yeah, I remember you. You have your 300-acre farm, you're growing corn, you have horses, and so here's like what you need. And it's now going to come back. And so this is kind of one of the easiest ways, by the way, if you have a chat application that you built and you said, well, I want memory, but I've already got my thing set up. Like, can I get this, can I integrate, Hindsight into it easily? And it's actually very easy to do. We have this wrapper. So if you're using like OpenAI, this shows OpenAI, this works with over 100 different LLMs, not just OpenAI. You can use this light LLM wrapper. And the light LLM wrapper will essentially just automatically do the integration for you with Hindsight. So any of the data that's coming in get written as memories. Any of the retrievals that need to happen happen automatically. And then you get kind of memory added with just a couple of lines of code here, just the import and the wrapper, and you're good to go. And then you'll have that all inside of your agent. And yeah, pretty easy to do. So let me go back here now. Let me see. There was a couple other questions I think that'll probably take us through the end of the time that we have. Is there a way to store propositions or raw memory while still allowing it to be retrievable? That was a question from Jameen, or maybe Jamin. So yeah, one of the nice things, and we kind of showed it. We kind of showed it here on this slide. This idea of these raw memories, where we have, we don't lose anything, right? So we don't have any lossiness that's happening. So you have your raw experience and facts, and actually there's kind of in here, we go into Hindsight, you'll see there's actually like the raw document. So like all of our chat history, for example, actually get fed in. Those all get processed through that processing pipeline that we had to turn those into the world facts, into the temporal links between things, into the semantic links, the causal links, all these type of things. But we never lose that raw data. That always allows us to go back and reprocess as well, which is important when we're doing consolidation, so that we take into account that underlying raw information in that consolidation process. So good question, Jamin. let's see, how is handling changing information? That is a very, very good question. So, because it gets to the heart of agent memory, which is this is the problem that a lot of people face when they say, I'm just going to store my conversation history. So like a lot of the like, we weren't the first memory system out there. There were other people that were doing agent memory. They were almost universally doing, like, implementing it as RAG over the conversation history. And the problem is exactly what you just described, where how do you handle that changing information? The way we handle that changing information is with this observation network. So the observations, every time new memories come in, we look across for related memories and we do we run memory consolidation. That allows us to deal with that changing information through the observation network. And so that's where we'll try to put together either, things used to be like this, but now they're like this. And then the LLM has a complete understanding, not just of, here are two independent memories and now I have to figure out what to do with them, but now here's kind of the narrative of how those puzzle pieces fit together. I don't know if I can unmute people self. You might just have to put that into the chat, your follow-up.
So Chris, it's like if we unmute one, we have to unmute everyone, so we
Yeah,
cannot.
that's okay. I know we're coming to the end of the time here. Anyway, let me just kind of look. How does consolidation scale as it grows? Yeah, so part of what we do, it's not entirely independent, but it's mostly independent of scale, because what we're doing is we're looking across the related memories. So we leverage those. We run sort of the raw data through the memory processing pipeline, and that's going to give us our semantic links, our entity links, and our causal temporal links. We use those to identify the related memories. Those related memories are what come back to form the observations and consolidation. So it's not like it's growing, big O of n with your size of memory. We're not doing a full table scan across there, which is why you won't see that huge performance hit, which is a good concern, but one that we thought of and one that we made sure not to do in a naive way. All the chain of conversations are interlinked. Yeah, cool. Thanks, Priya. Appreciate that. Mark Norman looks very powerful. Awesome, Mark. Yeah, try it out. We've got the the repo there on in the chat. So hopefully you guys got a chance to download that and clone the repo. If you run into any issues, put up a issue on GitHub. And I think with that, we're kind of at the end of time. So I don't know if you had any